All right, I see it as 1 p.m. Eastern Time. Um, Welcome to ICLR's February 2022 Friday Forum. I'm ICLR's Chief Engineer, Dr. Keith Porter, and I'll be moderating today. It's my pleasure to introduce our speaker, Dr. Craig Davis, a consulting engineer and principal of CE Davis Engineering from Santa Clarita, California, which is a community just north of the city of Los Angeles. I won't recap Dr. Davis's bio sketch here, which you can read on the announcement for today's talk. Instead, I'm going to tell you why I think we are so fortunate to hear from Dr. Davis today. To frame this, I want you to please think of a major change that occurred in your profession, some sort of sea change, something that happened within your career, and think back 10 or 20 years before that sea change happened. Was there somebody calling for it at that time? Somebody warning that it would be necessary, pointing to the empirical evidence, offering the logic that made the change desirable or practical, some sort of voice in the wilderness who ultimately proved to be prophetic or right? Now, my field in disaster engineering has a small handful of those people. And Craig is one of those people who's been building the case that when it comes to natural disasters like earthquakes, our current philosophy of design is inadequate. Our current philosophy is to protect life and to minimize initial construction costs. And we are finding that that isn't enough. We protect our lives, but not our livelihoods. We avoid small costs up front and pay the least possible first cost to build and maintain our lifelines, but end up paying far more later to recover when a disaster occurs. Now, Craig has been calling for resilient infrastructure for decades, and he's been helping to build the case for a sea change that's happening now in the United States. And that sea change is called functional recovery, which seeks to ensure that not only do we personally survive the main shock of an earthquake, but so does our economy. He leads projects for the United States National Institute of Standards and Technology and the Federal Emergency Management Agency that are going to turn that goal into engineering practice in the United States. And Craig's going to tell us about that effort. He'll speak for about half of our time today, and we will have this rare opportunity to ask him how functional recovery is going to work in the United States and what it might mean for the American economy and what Canada might learn from it. With that, a little bit of logistics. Would you kindly hold your questions to the Q&A period, although do feel free to chat them into the chat box, and I'll, I can relay them at the when we get into Q&A. I will now turn it over to Craig.
Okay. Thank you, Keith. Can you hear me okay? And you can see the screen, and I will minimize the pictures so I can see most of my screen. So I appreciate you guys taking your time to have me and to listen to this topic of functional recovery for lifeline infrastructure systems. And I think Keith set the stage pretty well, and I'll play off of some of his introduction as we go forward. The contents that I'll give you today is a little bit of background, some of what you're probably already aware of. I just want to set the stage. Then a national earthquake hazards reduction program in the United States study that was requested by Congress on functional recovery. Then I'll go over, give you an overview of lifeline infrastructure systems. What do we mean by them and what are their characteristics? Then give some functional or some recommendations for lifeline systems to achieve functional recovery and an example on what we need to do to develop a framework for recovery-based objectives, not necessarily in that order. So some of this will go back and forth, and it's not specifically outlined all in that way. But let me start with identifying what I mean by lifeline infrastructure systems so that you understand this as we go forward. So we'll start with the idea of infrastructure systems in general. Those could be defined as the physical and organizational structures and facilities needed for the operation of a society or enterprise. Now, lifeline infrastructure systems are a subset of that total definition of infrastructure systems, and they include water, wastewater, electric power, communications, gas and liquid fuels, and transportation at the core. So most that refer to lifelines are thinking of those. And in many cases, but not all, stormwater and inundation protection systems and solid waste are also included in those. So you might recognize these as the lifeblood systems for any modern society or community or urban area that helps make them function. And thus there is an analogy between what these systems do for a city and what different parts of our body do for our own health and wellness and ability to do things. So that's where the idea of lifeline comes from. Now, another important thing that I'll get to towards the end is that these are social technical systems, meaning that lifeline systems include the physical infrastructure, for example, the pipes and the pumping stations in a water or wastewater system, and the organizations that manage them. They are integral. So the pumping station will not work without a proper organization to make sure that it works. So we have to think about those integrally and equally, the organizational part and the hardened infrastructure part. So let me start with a little bit of background. And this is the part I inferred earlier that you probably are generally familiar with. So I'm not going to go through it in great detail. I just want to set the stage. So what is the motivation for thinking about a concept of functional recovery that I will define a little bit better in a few minutes? So in the United States, and I would suggest as well in Canada, we have a lot of natural hazard events that cost a lot of money. And that continues to increase as our populations congregate closer and closer into larger cities, and climate change is playing an effect as well. So I will focus on earthquakes, by the way, but these concepts are mostly applicable to almost all hazards. So even all the climate change related hazards and everything can apply. And that's embedded in what I'm saying on these couple of slides that I'll give you now. But for earthquakes, we have 150 million people in 42 states that are exposed to damaging earthquakes. There's a desire to reduce the vulnerability and minimize the losses for earthquakes and all other hazards, and improve the recovery time to the communities. That's just seen over and over again with all kinds of hazards. Now, for earthquakes in particular, the USGS has gone through and developed some scenarios to think about what happens when we have certain size events at different locations around the country. Dr. Porter has actually been involved with a lot of these, just as a side comment. And in all of those scenarios, it's important to understand that, you know, earthquakes are rare, but they're very devastating when they occur. So they don't happen every day or every year like a flood might somewhere around the country. But when they occur, they're very, very devastating. And the results of these scenarios, which are not the most extreme of earthquakes, they are expected size earthquakes, is that we have far more deaths, far more injuries, far more displacements, and far greater economic losses than what we would find acceptable. And the recovery times are not at the levels that we would like to see either, which plays into all of these other statistics that I show on the screen here. And then to get a little bit more specific, we have safety-based building codes. So I'm talking about buildings here, just as an example, because they have that all charted out a little bit better than the lifelines. But our building codes for anything across the United States, and I believe also in Canada, are really oriented around safety and then somewhat around property protection. And this is what Dr. Porter pointed out quite well, I think, at the introduction. So we have, if you were to build to current codes, which are quite robust, you still would get 20 to 40% of the code conforming buildings to be unfit for occupancy after a major earthquake striking an urban area, and 15 to 20% economically unrepairable, meaning that they can't be recovered. And the recovery time for that 20 to 40% could be quite long. It could be an order of months to years in many cases. And the older buildings that don't conform to current code, which is the mass of the assets that we have, will perform even worse. So we're not orienting ourselves towards what happens when we're in a disaster. We've just decided so far to current date to protect life, which is really important, of course. I'm not diminishing that, but we have to do better than that, because we can't we can't continue this way in our current situation with all the way we're going into the future. So we need to change the dynamic. Now, one major step in changing that dynamic, beyond people like myself that have for decades been pointing out that we need to worry about the recovery part of it, I'm by far not the only one. In 2018, the United States Congress reauthorized NEHER, which is the National Earthquake Hazards Reduction Program. It's a federal level program that initiated in the 70s, and it needs to be reauthorized every half decade or decade or so. And in that 2018 reauthorization, they ordered NIST, the National Institute of Standards and Technology, and FEMA, the Federal Emergency Management Agency, to work together to convene a group of experts to assess and recommend options for improving the built environment and critical infrastructure to reflect performance goals stated in terms of post-earthquake reoccupancy and functional recovery time. So the next few slides, I'm going to emphasize on the phrase of performance goals for functional recovery. And the outcome of this effort was put into a report, and I'm going to use the report as an outline to take us through the rest of the presentation. And there's some really important things in there, and I'll just refer to them as we go forward to highlight the outcomes of this very large group of experts that was put together to come up with this. So now talking about performance. So the net outcome is that we need to worry about performance levels. And I'm going to talk about them first for buildings and then for lifeline systems, just to help set the stage a little bit deeper. So there's 3 levels for buildings. One is reoccupancy, which was listed in the reauthorization. The second is functional recovery. And that begs the question, well, what about full recovery? So we identify it in terms of 3 of these. So the reoccupancy is the ability to safely re-enter and occupy the building while repairs are being made. The building services are not necessarily functional, meaning you might not have lighting, except for those required for the occupancy needed for safety, right? So you have to have it sufficient so that you can safely go in. But otherwise, it's just really intended to be a shelter, which is important after disaster. So if you have an earthquake and it's got heavy, severe cold or heavy rain or severe heat, right? You need some kind of shelter to get out of the sun or get out of the rain. So that helps. Now, in this concept of reoccupancy, the alternative sources for these building services might be permitted, like electric power could be supplied by generators, water could be supplied by bottles rather than through the tap. And the reoccupancy performance objective is the performance level within an acceptable time. Purposely vague at this stage, and that's the big challenge. What is the time for the recovery? And I'll get to that towards the end. How are we trying to address that? Then the next performance level is the functional recovery. It's a step beyond reoccupancy, and it includes restoration of building components and services to support a significant measure of the pre-earthquake building functionality. And again, this performance level is within an acceptable time. And then, of course, there's full recovery. That's the restoration of the building's pre-earthquake level of safety and functionality. So basically, the building would be able to do everything that it needs to do. Now, I'll point out here that functional recovery is an intent to allow the most important things that a building is needed for to be able to take place. So if it's a building intended to be a restaurant, then you can mostly do most of the restaurant things. If it sells groceries, you can sell most of your groceries, but there could be some limits to that. But essentially the building can be used for what people need to do their daily activities. So a business can actually move forward with its business activities, even though the building isn't fully functional. Then performance levels for lifelines. I'll talk about it in terms of infrastructure operability, which is that's the term I've been using for about the last 20 years. And I'll get to the full definition of that or an example of that towards the end. But operability is the ability of an infrastructure system to provide near normal services to a customer, sufficient for supporting community activities. This is, but the system may still be in a severely damaged state, meaning that you could, if you think of water, you could provide water to people so that they could do something, but there might be a lot of damage. And you might be able to do this because there's sufficient redundancy or interconnections or something like that. But you need to restore all of that redundancy for typical normal daily activities. And then, of course, there's full functionality. So functionality in general for Lifeline is the ability of the infrastructure system to work normally to provide a regular and reliable service. Now, full functionality would be defined when all repairs and all construction related to the event are done. And you may be at the pre-earthquake functionality, above it, or below it. But all work is now done. That's when you receive full functionality. Now, the report gives two formal definitions that I wanted to at least run by you on reoccupancy. And reoccupancy in the report is defined as the post-earthquake performance state in which a building is maintained or restored to allow safe re-entry for purposes of providing shelter or protecting building contents. Now, we're talking about lifelines here. So in the context of this presentation, reoccupancy only deals with the buildings within the Lifeline system. So in a large Lifeline system, a building would be considered a component that helps make it function, usually for housing equipment like a pumping station, or for office buildings or maintenance yards and stuff like that. And then functional recovery is a post-earthquake performance state in which a building or Lifeline infrastructure system is maintained or restored to safely and adequately support the basic intended functions associated with the pre-earthquake use or occupancy of a building, or the pre-earthquake service level of a Lifeline infrastructure system. So functional recovery is a performance state, which is in engineering terms an important phrase, which you would design to, but that has to be defined, and I'll explain that in a little bit, when the basic services are restored. And I'll define basic services throughout this presentation as well. And users receive these services essentially as prior to the earthquake and can use them to undertake their activities in a relatively normal manner. So if you think of that in terms of resilience, if you get all of the water, if you get water, potable water of a sufficient pressure and volume, then daily activities can be undertaken even before all of the work on the water system is completed, or the power system, or the natural gas system, and all of that. And so that's what we're trying to ingrain into these system operators, is that you can design a system to be damaged, absorb that shock, and recover for the community first, the services, without being constrained to making all repairs, which can take years. So that's the general concept of operability and functional recovery. So let's go over, where do we want to be? So when we did the work on the report, we identified that we need to protect against future losses. And to do this, we need a change in building codes, construction practices, and societal values. And functional recovery performance provides the link between the design of individual buildings and infrastructure systems and the goals of a community. So it's a major step forward to achieving resilience, but just doing this does not accomplish and create a resilient community. So I give a URL here, and this presentation will be provided for later, or this video anyway, will be provided for later use. And you can get this report, which is shown on the right, by clicking on this URL, or you could just Google NIST functional recovery or FEMA functional recovery. They have two different names or two different numbers on the reports, both of them jointly published, and each of the agencies freely provide this document. Now, the report has 7 major recommendations and many tasks associated with them. The first recommendation is to develop a framework for post-earthquake reoccupancy and functional recovery objectives. The second recommendation is to design new buildings to meet recovery-based objectives. The third is to retrofit existing buildings. The fourth is to design, upgrade, and maintain Lifeline infrastructure systems to meet recovery-based objectives. And the fifth, sixth, and seventh are respectively to deal with recovery planning, education and outreach, and financial resources. Now, I'm going to talk about recommendation 1 first, because it's the core and basic idea for everything that follows. I'm going to skip 2 and 3, even though they are important for the buildings within a Lifeline system. And then I'm going to focus a little bit more on the 4th recommendation for Lifeline systems, and then address the parts of chapters 5, 6, and 7 that deal directly with Lifeline systems. And I'll skip parts of those that focus only on the building aspects. So where do we begin? We begin with developing a framework, which was the first recommendation. It's coordinated action is required across all of the recommendations, and it helps set that coordination. But progress can and should be made in all of the areas at the same time. There's a lot that could be done, and not all of it is dependent upon recommendation 1, the framework. But you probably can't fulfill the vision of what this work, the outcome of this work is looking to have, if you don't fully accomplish the framework. Because the framework will provide the core policy, including key technical information to form the basis for the other activities. So now I'm going to go through what I referred to earlier as the outline. And for recommendation 1, it was to develop a framework for post-earthquake reoccupancy and functional recovery objectives. It has 3 major tasks: to develop a policy for recovery-based objectives, where we need to target recovery times for key functions and services. And those may vary for new and existing buildings or new or existing Lifeline systems. And we also have a task to develop a design criteria for recovery-based objectives, which will deal with the codes and standards for both buildings and Lifelines. And we may end up with separate topics and separately addressing the aspects for buildings and Lifelines, but they need to be in parallel and they need to be coordinated. We need to keep checking back with the other sides. When we're dealing with Lifelines, we got to check in with the buildings to make sure that these are consistent. If they're not consistent, we will not achieve a resilient community. And then lastly, we need a task to determine the appropriate hazard levels. I'll explain those in a little bit more detail for you.
Hang on a second.
Yeah.
Before you do, Craig, hazard has a technical meaning for us engineers, and it's important here. So I wonder if you'd explain it to everybody else what you mean by hazard.
Yeah, okay. Okay, so in earthquakes, it actually has a lot of connotation as well. So I thank you, Keith, for pointing that out. So first of all, hazard, an earthquake is a hazard. So if an earthquake strikes, if we feel an earthquake, then a hazard, that earthquake hazard has struck. Now, the level means that what size of an earthquake. So what magnitude was it? What level of shaking did you have? Was it close to you? Was it not close to you? So that's generally referred to in terms of intensity. So maybe you've heard of earthquake intensity. But then there's other hazards that come from that. So there's when an earthquake strikes, it's because there's been a big fracture in the earth along a fault. And so if that fault ruptures to the ground surface, then there's a surface rupture hazard associated with the earthquake. That fault rupture creates the shaking. So there's a shaking hazard. that shaking may knock loose some slopes, and so you would have a landslide hazard with it. It might cause a geotechnical issue with liquefaction. So there's liquefaction hazards, and then liquefaction itself can create other hazards like other types of movement, ground movement, settlement, ground settlement, and horizontal movements similar to shallow landslides. There's tsunami hazards that might occur or situ hazards if you're near a big body of water. And so that's what I mean by hazard and hazard levels. And each of those could occur at different levels of intensity. And so engineering wise, we need to worry about what are the hazards that might occur? What are we exposed to? And what is our vulnerability to them? And how big is that hazard? Meaning, what is the level? So hopefully that's sufficiently clear. Keith, do you think I covered that well enough?
Yeah, that's great. I mean, it seems like you're saying that the hazard level is basically a measure of what the environment is doing to our stuff, what the earth is doing to our pipelines and our buildings, or in other perils, it might be what the hail was doing, how big the hailstones are, and in a flood, how deep the flood water is, and so on. What the environment is doing to the built environment.
Yeah.
The natural environment is doing to the built environment.
Right. Yeah. Very good. Thank you.
Thanks.
Okay. So now task 1.1 under the framework is to develop a policy for recovery-based objectives. So the recovery time, I didn't start that off right. So we need to identify what recovery time is needed for which functions and services so that we can meet the community resilience goals. So we have all of these different social activities, and the buildings and the lifelines support those social activities, and they provide some level of function in the community. So we have medical services, we have fire services, there are businesses of all types, industries of all types, and each of those provide services. So in another presentation, I identified that we have services for services. So Lifeline systems provide services to businesses and industries so that they can use the products from the Lifeline systems to prepare and provide their services and products, which are given to others to provide services and products and so on. And so we need to think of this, of how everything interrelates and the importance of the basic aspects of what services provided by Lifelines do for the rest of the community. Now, not everything is needed right away. So not all functions and services of a Lifeline system or a building are needed right away. And not all things from businesses and industry and other community services are needed right away. So we need to parse these up and make sure that we get the most important things underway when they're needed. And that can be quite complicated. So we need to identify the target recovery time that relates to these functions and services so that we can give the community what they need when they need it. And what we're showing here in a diagram is a timeline that was, it's from the National Disaster Recovery Framework that the Federal Emergency Management Agency organizes. And it identifies that there are multiple phases. And we can think about these in terms of the phases in the recovery during and following a disaster. So there's a short term, which is usually taken care of in days, and that's usually the emergency response phase, and you got to get the disaster under control. And then there's an intermediate phase, which happens usually in weeks to months, where you're beginning to get things underway and somewhat back to normal, but so that you can start recovering your functions. But there might be sufficient amount of damage that takes a very long time, in the order of months to years, to get things repaired, even for moderate size events. In some cases, if you're very vulnerable, it could take months to years, even for smaller size events. And so we could think about the recovery time and what we need for different functions and services in terms of short, intermediate, and long-term phases, and what emergency managers and community activists would be doing in these timeframes on a standard basis. Okay, so developing a policy for recovery-based objectives. What recovery time is needed for what functions and services to meet the recovery goals? So what functions and services are essential to critical to recovery for today's communities? Things change over time, as we know. And so when we thought about and built the original codes, which started in the 30s and mostly evolved in the 70s, it does not necessarily reflect today's understanding and the way we operate today. And we'll point that out in the bottom bullet here. But so current codes use a concept of risk category to apply higher design criteria and performance goals to functions and services deemed important or of a higher risk. So risk category 4 applies to what they define as essential facilities, which generally are the hospitals, ambulance, fire, rescue, police, emergency communications and operations, and those types of things. But unfortunately, the current building code definition of essential does not reflect overall recovery needs. And we can just reflect on what's going on now with COVID and actually see this. So there's urgent, we know that we have urgent and routine healthcare, but we include hospitals, but we don't include pharmacies as essential. We don't include food supplies as essential. We don't include schools as essential. But we do worry a lot about the schools because it's unacceptable for that to have a catastrophic failure and cause a lot of death to children. We don't look at construction as essential, although that's necessary for recovery. We don't really look at commercial or retail as essential, and some of that might not be, but some of it might be some of the most important things right along with a hospital or a fire department. And so we need to really dig in deeper and understand what these social functions that are necessary for functional recovery so that we can make resilient communities. And then when we move on to task 1.2, it's to develop a design criteria for recovery-based objectives. We need to identify what design will achieve these recovery objectives. So think about it in terms of at what level would I design a pumping station in the building that houses that pumping station to ensure that I could actually recover it after an event. So it can sustain a certain amount of damage. So from an engineer's perspective, we worry about, well, how much deflection can it have before it cracks too much or might have a permanent lean, which we don't want. But yet not have to spend so much money that we don't have enough money to ensure that we could afford other things to be functionally recoverable as well. So where's that optimum stage? So the way we're thinking about it is to use functional recovery categories, which are a similar concept that we're used to for the risk categories I just explained. So we're thinking of starting with this table on the right or something like it and make a simple approach to group the function and services based on the relative recovery priority. And in the future, make some solutions and basically refine it, which is essentially the way we do with the building code now. This building code changes every 3 to 5 years because we keep learning, doing research and find things and how to improve it. So we don't want to solve the problem before we get started because that will take decades. We want to get started with what we know because we know enough now, and then continually refine it as we go, make more improvements over the years and decades. So this table identifies functional recovery categories, the target time frame, so in hours, days, weeks, or months, or years, and during what phase do we need things to be recovered. So in the near term, for example, we need emergency response and rescue, safety, security, and event stabilization, and so on. You can imagine the hierarchy here if you haven't read it already. So, but for time, I'm going to move on. So then in task 1.3, we need to determine what hazard level. So as Keith and I explained earlier, so what level of an event? So what size of an earthquake and the associated additional hazards or cascading hazards that might come from that do we need to worry about to design to? We can't design for the worst case because we can't afford it. And plus, those are extremely rare. So those might not occur but every 10,000 years. And if it's going to occur 10,000 years from now, these buildings and lifeline systems are not the ones that will be there at the time. It would be something quite different. Hopefully humans are still around in 2,000 years, but if it's going to occur in 500 years, well, think of buildings we got 500-year-old buildings here, but very few. But think of Europe, there's a lot. So a lot of our infrastructure will still exist in 500 years. Certainly in 100 years, we design things to last 50 to 100 years. So do we design for a 100-year earthquake, 100-year flood, the 500-year, the 2,000-year, the 5,000, 10,000 year? Big question. So the more robust the design is, the easier it is to survive. And even if it's damaged, the easier it will be to recover. But we have to optimize this. And we need to worry about at what levels do we design each asset that allows the community to do its functions. And in a system, it's a bunch of assets connected together. That's what lifeline systems are. So at what level do we design each asset, and are all assets at the same level? Maybe some aren't as important as others. So think of an asset as a pipeline in a water system. Not all pipelines are actually equal. And by the way, I'll use water as an example as I continue through this. I worked for 32 years at the LA Department of Water and Power, and so that's of all the lifelines, that's the one I know the most. So I will tend to refer to examples for that. And then we need to establish performance goals for existing and new, and the new, existing and new. And the new might be a little more strict than existing because it's harder to go back in to make the changes. So then we need to worry about, we need different performance goals and recovery times. And can we do what they're currently doing in the building code by setting one design level earthquake and assume that that covers everything, even if the earthquake is higher or lower? Or do we actually need to do maybe 3 different levels of design? One for a more frequent earthquake, one for what they currently call the design level earthquake, and another design and analysis for a more extreme event. It's easier, of course, if you only do one, but for lifeline systems, it's a little difficult because they're spatially distributed, which I'll get to a little bit further. So another difficult question that we need to worry about. And the issue there is, if you have a large earthquake, if you have a large system, not earthquake, I meant a large system, and an earthquake strikes at any level, and it's in the middle of that system, and that system covers the whole city, if you're on the outskirts of the city and the earthquake struck on a different side of the city, you might feel just a limited amount of shaking. But if you're over on the side of the city where the earthquake struck, you would be shaken very, very hard. The harder shaking will cause damage to the lifeline system in that area, but the lighter shaking on the far side of the city might not cause any damage. And so you can design for that event, but what if there's the opportunity of multiple types of earthquakes within the system? So maybe another earthquake would occur in the area that I just explained would have light damage for earthquake 1. For earthquake 2, it might have heavy damage. And if we need to worry about both earthquakes, you can't do it with just one design of it. And that's the concept we're having to dicker with here and figure out what's the best way to do it. So now let me step back a little bit from the report and talk again about lifeline infrastructure systems to set the stage for our recommendation 4. So I already showed you this slide. I just wanted to flash it in front of you again, just to get you back on the same stage. The lifeline systems are water, wastewater, electric power, communication, gas, liquid fuels, transportation, stormwater, and solid waste systems. Let me give you an overview of some of their characteristics to set the stage for why certain recommendations and things that we need to worry about exist. So lifeline systems are large geographically distributed systems. Some cover multiple regions, states, or even countries. There are lifeline systems that cross between Canada and the United States, and United States and Mexico. And even over in Europe, when you think of communication systems, they're international now. They're even out in space. Lifeline systems are made of numerous interlinked specialized components. So it's not like a common type of building over and over again. There's all kinds of specialty things, and all those specialty things are linked up, and they have to stay linked so that things will work and the services can be provided. Those those specialized components are designed and built over long time frames using different materials and standards and procedures and so on, which makes things a little bit more difficult when you think about the vulnerabilities. Lifeline systems consist of a variety of subsystems, and those subsystems may have separate owners and operators, and they could be an intermixing of both public and private for different subsystems. So, for example, you might have a private water supplier that goes to a public water treatment, back to a private water distributor, back to a public water distribution system. And that would be the whole system made of those 4 subsystems. And so we have to worry about the public and private and how they interact and the different regulations that come from them. And we have to coordinate all of that. All Lifeline systems provide services, and services really is the key. But not all services are for buildings or other Lifeline systems. They provide services for agriculture. They provide services for the environment. There's all kinds of services provided by different Lifeline systems. And that gets forgotten in some of this by many engineers and politicians. Lifeline systems are interdependent, meaning that the performance of one affects the performance of others. Part of the interdependencies are the co-locations, meaning that the proximity and failure of one can result in unintended damages to others. The failures in a single system can result in cascading failures in others that can cause public health and safety concerns, including flooding, explosion, fire, electrocution, contamination of water, blocking mobility and communications, and a wide loss of services. So I show one example where almost all of this occurred on Balboa Boulevard in the 1994 Northridge earthquake. This was a large thoroughfare. It was actually a main evacuation route in general, but it couldn't be used because you see all the water and the fire in it. It's also a major utility corridor. And so there was liquefaction and ground failure here that broke natural gas lines and water lines. And that ended up sparking a fire, which caused damage to electric power poles and so on, and burned down a few houses. And so you can see all of these problems occurring in just one location from the co-locations of the many Lifeline systems. So these systems need they need intimate coordination between all of the systems, but yet each system tends to operate in silos, and I think that's more of a human nature issue. It's easier to just deal with your own issues than integrate with others, but they have to be integrated. When it comes to regulations, there are numerous regulations and regulators. There is no single regulating authority across all lifelines. Some lifelines have multiple regulating authorities that cover local, regional, federal, state, and they may cover similar or different aspects. And if they're covering similar aspects, that could become a problem. Reporting to multiple regulators is also an issue, but it's just necessary, I guess. The regulations may differ between public and privately owned systems, even though they do the same thing. Most regulations deal with safe and reliable operations, but not extreme events like earthquakes. Earthquake regulations, when they exist, differ between systems and across state lines and across different countries. And some earthquake regulations deal with specific critical components like nuclear power plants and dams, but not the rest of the system. Now, earthquake-related performance criteria is mostly related to the structural components, meaning buildings, bridges, piers, and control towers, but not, for example, the pipelines and so on. And there are relatively no system-level seismic performance criteria dealing with services. And most systems are not designed for earthquakes, but a lot of components might be. So I'm making a big distinction here between designing the system as a whole and designing each component that builds up and makes up the system. So there are a variety of manuals, guidelines, and standards, but most don't actually address earthquakes or other hazards other hazards. Those covering earthquakes are inconsistent with the systems and within systems, and especially across systems. Few manuals, guidelines, and standards address post-earthquake recovery times. And those that do or imply are inconsistent, meaning that if you follow one, it might not be consistent with another guideline. And lifelines generally are not designed to provide more reliable service to any specific customer. It's just, how do you get the services up? And then, of course, aging and deterioration is a significant issue with all lifeline systems. So that's a lot of issues that most of those actually are not associated with buildings. So lifelines have a lot of different issues than what most people are familiar with for buildings. And that needs to be understood so that we could address this properly. So including recovery objectives for lifelines means that we need to be designing beyond safety, which is our current state. We're only dealing with safety and property protection to a certain level. And then addressing for all lifelines, the geospatial hazard exposure, interdependencies, operations in silos, the lack of system level design for services in extreme events, the deterioration, the range of regulatory requirements, and the limited or lack of design manuals, guidelines, and standards. So now let's take that and move into recommendation 4, which is design, upgrade, and maintain lifeline infrastructure systems to meet recovery-based objectives. So now I'm back into the report recommendations. And I need to state that what I already covered for recommendation 1, which is the framework, needs to be addressed so that we can properly address all of the aspects in task 4. So, in recommendation 4, which has several tasks. So task 4.1 is to provide a national level guidance on regulatory authority across lifeline infrastructure systems. So we need to review the regulatory authorities across all lifeline infrastructure sectors, define the overlaps and gaps at local, state, tribal, and federal levels, create national level guidance, developing a governance structure to provide a consistent set of regulations across all lifeline infrastructure systems. Now, the basis for this task is that we have no common jurisdictional authorities, that some lifelines may have no regulatory authority to oversee or mandate functional recovery improvements, and we need consistent, not conflicting regulations. So we need to do a thorough review and make sure things are good. Then for task 4.2, it identifies to evaluate the ability of lifeline infrastructure systems to meet recovery-based objectives. We need to include the entire system, from source to delivery or collection to discharge, regardless of the different subsystem owners, and include the interdependencies and all plausible earthquake hazards. Both of those have, well, the interdependencies are that, as an example, there's dependencies and then interdependencies. So dependencies is more general. Let me explain that a little bit. So for example, if you are pumping groundwater for your water system, you need electric power. So the water system is dependent on the electric power. So if the electric power goes out and there's no damage to the water system, you still might not be able to function. A water system might not be functionable just because it loses power. So that's a dependency. Interdependency is a little more complicated in that, for example, maybe you have a power generator in the same location that I just referred to, and you need to pump that groundwater for cooling and creating steam to generate power at the power plant. But you need the power to create the pumping. But you need the pumping to create the power. So that's an interdependency. And that's a little bit more complicated to resolve. And that covers across all different lifelines. There are interdependencies and interdependencies amongst them all in different ways. Also for 4.2, we need the results of evaluations to be transparent. And we need to use the current technologies because we haven't fully developed all the best technologies for running complicated analyses, but we need to use the ones that we have now to get started. And as we improve those technologies, periodically reevaluate using the better technologies. And also the systems evolve over time, so they need to be evaluated simply and only for those purposes. Now, the basis for this is, from what I explained earlier, is that most, if not all, lifelines do not know how their system will perform in an earthquake or how long it will take to recover. The entire system with all plausible hazards are not normally included in the evaluation. So to explain that, normally that include the entire system from source to deliver. They usually evaluate a subsystem, not the whole system. And when they're doing that, they also don't normally, if it's even done, cover all hazards. So they might skip fault rupture, or they might not address landslides, or they might not address shaking to the right level, or they might not address liquefaction. So all of those that can occur, all those hazards that can occur with all of the entire system needs to be evaluated, which can get quite complicated. And customers and authorities are not usually informed of the results, which is even more important. So now the community can't prepare if the system is going to be expected to have damage and loss of services for a long period of time. The community should know that so they can prepare accordingly. Or if the system is expected to survive, then they should know that. So again, they can prepare accordingly. Then task 4.3 is to develop a national level seismic design standards for lifeline infrastructure systems to meet recovery-based objectives. So we need a consistent set of guidelines and standards and codes for all lifeline infrastructure systems. And these currently do not exist, even within one type of system, much less consistency across all systems. And that's really important when you think of the interdependencies. And as an example for that, a current issue is that hospitals are designed to a higher level than bridges. But many hospitals actually rely upon the transportation to get people to the hospital in an ambulance, for example. And many of those ambulances need to cross a bridge. Now, if that bridge is the only access, and sometimes that bridge is part of the hospital, that bridge might be designed to highway standards and the hospital designed to code standards. And everybody thinks that's okay, but they're not consistent because the bridge would be designed to a 1,000-year earthquake shaking return level and the hospital to a 2,500 year. And that would mean that if you receive the 2,500 year, that you would expect the bridge to be damaged, which means that you can't use the hospital because nobody can get into it, right? So that's why consistency is needed. And then we also recommend to create regional lifelines councils. Now, what are lifelines councils? They would be a group of local lifeline organizations that would meet and talk about how they do things, how it would interrelate with the other lifelines. And that would go a long way to resolving the interdependencies issues. We got to break the silos to address the dependencies and interdependencies. And I'll skip the last line there. So I'm going to pause for a drink here. A drink of water, that is. Okay, so now I'm going to move on to the last three chapters, enabling mechanisms. And some of these actually deal directly with what this organization that I'm talking to here does. But the enabling mechanisms cover planning, education and outreach, and financial resources. So this involves the organizational aspects or the social aspects of the social technical system. Most of what I described are the technical aspects or the hard infrastructure of the lifeline social technical systems. And we need to address both of these equally. So what I just explained is really important. And what I'm going to explain is equally important, but engineers normally don't address these next three sections wholeheartedly. So planning. Planning is needed to achieve recovery-based objectives beyond that achievable by design and construction alone. We need to be making decisions before a disaster about how a lifeline system will work, and thus the community will be able to recover after the disaster. So we have to have an imagination and think about what actually could take place and how to resolve those issues in advance. So recommendation 5 states to develop and implement pre-disaster recovery planning focused on recovery-based objectives. So for lifeline systems, we're putting the local lifeline system leadership at the helm to plan their system. They need to think about this. And that could be done possibly by integrating resilience managers or other assignments into the responsibility of existing systems, such as the director of the system planning and development. And so for lifelines, this planning would be undertaken by each lifeline infrastructure system authority individually, and they should do it individually for their own system, but also as a part of a larger group effort if one could exist. So like a community planning and community resilience planning and so on. The Lifeline systems need to engage into that, need to collaborate with the communities they serve. All of them, even if you're very large, some electric power systems in California, for example, cover half the state. They cover a lot of communities, huge amount of the population. They need to deal with all of those communities. And so it could be an enormous effort for the larger agencies. So task 5.1, develop and implement pre-disaster recovery plans, means that we need to be incorporating recovery-based objectives into existing plans. Now, these are a higher level thing. This usually isn't something that only a Lifeline system would be dealing with. So a Lifeline system isn't really creating community level comprehensive plans, land use plans. Those are usually dictated by the community planners, and that could be at the state or local levels. And developing and implementing community resilience plans using the NIST Community Resilience Planning Guide. You can Google that and find that. That's a good document for helping to plan for resilience, and incorporating recovery-based objectives into hazard mitigation plans. So this highlight at the bottom is that the Lifeline systems organizations need to be involved and engaged in these broader activities. So they should influence these activities, and they should learn from them and implement the results of those plans into their activities. And then task 4.2, create and promote seismic continuity programs. We need Lifeline systems organizations need to prepare business continuity and or continuity of operations plans. And these are above and beyond the emergency response plans and exercises that they should currently have in place. That's very important. In task 5.4, plan for sufficient staffing to expedite post-earthquake recovery. Don't wait for the event to know that you're going to need more people to recover. The resources are huge. I was a responsible party for recovering to the Northridge earthquake, the water system in 1994. And so I understand that quite well. So we need to highlight the staffing issues to make them a priority for action before an earthquake occurs. We need to recognize that temporary increase in staffing capacity after the earthquake is important, and they can plan by creating mutual aid and mutual assistance agreements. You can do that now with people that hopefully wouldn't be affected by the same event. And then we have education and outreach. That's needed to facilitate the demand by stakeholders for the uptake of voluntary measures for regulatory change, and maybe not even just regulatory, and for regulatory, yeah. So we want the constituents or the users of these Lifeline services to want the agencies to do these activities for functional recovery. And we need to start by understanding the customer base and what their pre-existing knowledge is and their propensity for change, and maybe modify their propensity for change so that this change could be made. So we need to educate building and Lifeline infrastructure system stakeholders about earthquake risk and recovery based objectives. We need to be giving all citizens the information on the earthquake risk and the common secondary hazards that earthquakes might trigger, and the associated cascading events. I explained those earlier. We need to explain the results of the analysis, for example, from task 4.2, so that people know how their services may be affected and they can plan accordingly. And we need to make customers and users aware of mitigation strategies for achieving recovery-based objectives and help make educational accessible and actionable. So we need to educate design and construction industry professionals. The same thing. No. Educate design and construction industry professionals about the earthquake risk and recovery-based objectives. So this increased knowledge means that we can do better for design, construction, and retrofitting for all Lifeline systems to meet recovery-based objectives. And we can provide tips for communicating the benefits of reoccupancy and functional recovery to the end users. That will help with maintenance and as well as the base design level and construction. And then lastly, we have financial resources, of which a lot of that education would actually be driving towards. How do you get those financial resources and make demands for providing those? So we need that to implement functional recovery design, construction, and retrofitting actions in pre-disaster recovery planning, as well as the response and recovery activities during a disaster. So recommendation 7 is to facilitate the access to financial resources needed to achieve recovery-based objectives. By shifting to recovery-based objectives, there is money up front for planning and mitigation activities. Those who bear the cost, such as the Lifeline systems, must have access to the financial resources to accomplish this. And despite an incremental increase in the upfront cost, future costs should decrease. So over time, there's a net savings. Mitigation saves, as Keith will tell you over and over again. So what costs? We can save costs by reducing the losses associated with the damage, business interruption, and reduce services from lifelines. We can also reduce the operating and financing costs associated with recovery. And the Lifelines organizations need access to cash reserves to carry through the post-event activities. So they need ready cash at hand to deal with the loss, because they will have a loss in revenue post-event, and they need to fork out cash right away for materials and people who will be going out and making the repairs of these damages and restoring the services. So they need to have agreements and understanding, and maybe cash reserves in a safe in their office building. And then task 7.1 is to develop and deploy pre-disaster financial mechanisms to achieve recovery-based activities. Now, this particular slide might have some meaning to this organization that I'm talking to. So we need to offset costs using financial incentives, insurance discounts, and public sector assistance. So we need to offer these Lifeline utilities reduced insurance premiums if they're upgrading their systems. A public utility commission policy is probably needed that allows for small rate increases. And we need to enhance bond ratings. And we need federal and state and local grants and loans. So this is broader than the Lifeline systems, but the Lifelines need to engage and be involved with the state and federal agencies, as well as the financial and insurance sectors. So relative to insurance, one way you might think about it, again, going back to water, if a water system has improved its ability to fight fires on a normal basis, as well as after a major event, then the expected losses and premiums due to fire would be reduced. And the idea would be that could you use some of that money up front, or could we get bonds to invest into these improvements, knowing that the residents or the customers of that water system would have reduced premiums later. So if they know there's an offset, they'd be willing to say, all right, if I'm going to have reduced premiums, I could pay higher rates, maybe just by a penny a month, so to finance these things. So it's different concepts, some of which I'm probably getting far outside of my knowledge base, but that's one example that has come to me at many different times that I wanted to express. So then another component is to develop and deploy post-disaster financial mechanisms to achieve recovery-based objectives. And this takes into concept that we can't prevent damage in a major earthquake. There is no such thing as earthquake proof. There will always be something to repair and recover. And in a major event, there's no way we could conceivably believe that we could design a large, complicated Lifeline system to not lose services. I think that that's just a reality. So we need to accept that as a basis and understand it. And so even in the best case scenarios, financial resources are needed. And we need to enhance the existing mix of federal programs, private borrowing and savings, and private development, charity, and private insurance. And Lifelines organizations need plans on how to have the funds at hand immediately after the disaster. Okay, so Keith, here, I got a few more slides that give specific examples. I just wanted to check in on time before I go further, because I could stop here, but this gives a little more detail on what we're doing, and I'll leave that up to you.
Well, I think that perhaps at this point we should stop and have a little discussion. I think that we're, we're so down into the weeds that we've lost almost all of our attendees. So maybe we should just stop now and use the last 25 minutes for a conversation between you and me and Dr. Gordon McBean, who's our last attendee, to come out of the weeds and come back to the sort of the big picture. How does that sound?
That's just fine. So I apologize if I've lost the audience.
It's it's always peril when you're presenting technical engineering stuff to a non-technical audience, and perhaps that's where we should take our conversation now, because Dr. McBean has spent much of his career straddling the boundary between science and policy. He has had to communicate science to policymakers at the ministerial level of the Canadian government. So Gordon, I'd be grateful if you'd come off mute and give us your thoughts about what part of Craig's project should interest policymakers. How would you suggest telling the story that Craig is trying to tell to make to appeal or to grab the interest of the people that he needs to talk to?
Well, thanks, Keith. Can you hear me? I don't know how to operate. I turned it off. It doesn't say mute.
No, we can hear you just fine.
Yeah, you don't need to see my face. That's good, because I don't have a tie on or anything. No, it was interesting. I got somewhat, let's say, not fully following all of the engineering stuff, since I have two brothers who are PhDs in civil engineering and a daughter who's a chemical engineer, but I'm not into the engineering technology. But as Keith said, I was for 6 years the Assistant Deputy Minister for the atmospheric part of Environment Canada. But anyway, and spent a lot of time since then also dealing with the political issues of how do you motivate, let's say, actions. And in Canada, and I think it's similar in the United States, one of the biggest challenges is the multi-level governance system, so that you have a federal government with certain responsibilities, a provincial governments which have different and overlapping responsibilities, and the local municipalities which have a range of interests and difficulties, responsibilities legally and things. And as I was informed when I first started with the civil service, I was an academic prior to that at University of British Columbia professor. One of the senior assistant deputy ministers told me, as a matter of information, he said, you must understand the rules for every politician in Canada, and I suspect it applies in the United States and elsewhere. The first rule is get yourself reelected. The second rule is get your party reelected. And then he laughed and jokingly said, and the third rule is don't forget the order of the first two. And so I think one of the key things, and what you were talking about, is important in terms of presenting it in a way they realize the impacts, not decades away, but or at least the risks of impacts that will happen in the near term within, as one minister asked me at a briefing session, he said, well, what will happen between now and the next election, Gordon? And I think we need to, unfortunately, recognize that reality in order to motivate action among politicians, and quite frankly, people in general, because they get motivated by things where there will be impacts on them relatively soon, as opposed to in the distant future. But as I always point out, we're doing this thing, and I pointed it out to that minister asking the question. I said, we are doing it for our children and grandchildren, and all children and grandchildren around the world. And as a result of that, my two grandchildren at that time got their picture put on the front page of one of our major newspapers in Canada as an example of why scientists advocate for action. So anyway, enough of me talking. And just to say that I think what you were talking about, and although it gets complicated, was very much the important way of showing the various, say, actions you can take to make it so that when you do have a tragic event, first of all, there's less impact and you recover more quickly and get back to normal without having too many impacts on the health and otherwise of the citizens. So I'll stop there.
So if Craig's project is going to produce materials that, I mean, he's got to lay out some really detailed technical procedures for engineers to follow. But he also has to make it so that, that the engineers, he and NIST and FEMA, can sell this thing to the public, to code officials, to Congress, etc. What sort of, should he be building material into his report where the policymaker can pull out something and say, this is going to help me get reelected, or this is why I should, this is part of my election campaign. How do you make building codes and the sea change in design a political issue?
Well, I think you can try and do it by showing although there are costs, that the benefits that are there, that, and many of the studies on climate change adaptation, the analysis being done and redone show that, for every dollar you invest now or in the next few years, you'll get several dollars return over the next decade in all likelihood. And I think we have to make those kind of, let's say, arguments more understandable to recognizing that most politicians don't have degrees in engineering or science of any kind. They come from different backgrounds, and it's, well, I think the whole question, one of the issues that I think is very important is, and I must admit I wasn't listening to every word you said there, Chris, but I think the idea, that the benefits to the health of people and their children, and the avoidance of impacts is an important thing. More so, at least personally, anyway, I'm more concerned about that than I am of dollar costs. And and there isn't really a way of putting dollar amounts specifically on the health costs, particularly longer term and mental health issues and that kind of thing. So it's
yeah. So one of the things that we are focusing on that was going to get a little bit more detailed, I just want to have an overview, is that you prioritize based on basic human needs. Mm-hmm. Which, so you, in a water system, if you lose it, people normally plan to get their water out of the tap. But if you can't do that, people will start dying in 3 days. So somehow you have to have a plan, either to get water through the network or deliveries in trucks that's potable that people can go get, or deliveries to houses with bottles. Mm-hmm. And actually that could be used as a cost savings measure, that if you knew that you were able to do that, which is done all the time, then do you actually have to have the system upgraded to deliver water to every house after every major event, whether it's earthquake or flood or something else, when you can do it in another way? Because that's very costly. Maybe you could spend that money elsewhere. Maybe you want to spend your money to make sure that you can get water to every hospital, and you can isolate that if you need, and not worry about the majority of customers throughout the residence right away. Of course, you need to worry about them, but not right away. So in that initial phase, the first week, don't spend all your time on the masses. Get them bottled water, and spend your time on making sure you have firefighting water and water for emergency evacuation centers, hospitals, and the other medical systems that support that. That's the basic idea that we're trying to bring forward in the framework. by implementing it that way.
Craig,
Oh, that sounds appropriate. And I think, but while I think of it, just in case I forget before the end, thought I heard Keith say that you were from the California area at the beginning, or you're Los Angeles, is it? Or
Yeah.
Do you know Roy? Sorry. Yeah, Roy Herndon.
No, I don't.
He's the chief hydrogeologist with the Orange County Water District in Fountain Valley, California.
I'm on the complete opposite side. So in driving time, that's about 5 hours, and in the distance is not so far.
Okay, well, no, the reason why I just brought his name up is Roy. Because one of the things I was recently involved in, I was chairing a review panel for the Japanese research agencies who integrate, they have a major comprehensive disaster risk reduction research program underway in Japan involving, well, they never told us how much money, but huge teams of people working on issues of water and structures and things. And Roy was, I didn't select the panel members, but Roy was one of the members and one of the more impressive members of the panel. The others were, there was 2 Americans, 1 Canadian, me, and some from Japan, well, 1 or 2 from China, Japan, Taiwan, etc. But he was a very interesting guy. I just remember his name, and I've never met him other than by Zoom. And I was exchanging emails with Shrew Shrushian, who you may know at UC Irvine, about just before I started my listening to your call. Do you know him?
No, I don't, but I might end up meeting both of them because I'm going to get involved in a research program at UCI.
Sorry, this is interesting, but I want to interrupt the conversation about mutual acquaintances and bring it back to sort of high level things that ICLR and others can take away from functional recovery. And one question that occurs to me that's big picture is that the way we design now was called into question as soon as the way we design now was created. As soon as load and resistance factor design was developed in roughly 1980, people said, well, this isn't good enough and we got to do better. So the complaints about current design date back decades, and we're doing this now. We're working toward a paradigm shift 40 years later. My question is why? What do you think happened that brought about this, the charge from Congress, the urgency? Why are we doing this now? How might we have done it 10, 20, 30 years ago? What could we have done better in past decades to accelerate this conversation?
I don't know about what we could have done better. It's not off the hand. But one thing that I am familiar with is what changed the dynamic was in part the Northridge earthquake. That was, I can't say with all certainty, but it was a major event. I don't know if it was the event, but it was a major event that people began to realize, what do you mean my building isn't usable? It was designed to code. And there was a significant economic impact that people didn't expect. And people were dislocated for long periods of time. And there was a huge argument about why doesn't the code cover this? Nobody told me that when I built this. And then there were even code issues with steel buildings, Keith, that you're probably well familiar with, and other things that really shocked the public. And so I know from personal experience that event began to evolve things. But one of the problems that this particular issue fell into is that over time, that all subsided, right? So there's a moment in time that you get after a major event to take action, and then politically it just goes away. There's no more funding for it, research, things just go in different directions. But one of the other things that, this is from personal observation, and I think the scenarios, Keith, the shakeout scenario, you were involved with a lot of that, but my own observation and my career changed because of some of those things. And they were very helpful in educating the public, but it had to be done right. you don't have to have an event to get the public's imagination and the leadership's imagination to say, I don't want that to happen. Now they're thinking about what can I change for the future as opposed to what has already happened. And another factor that comes into that, if it's already happened, you know, it won't happen again in my lifetime. Well, that's not true either. We know that.
Mhm.
And that becomes a factor after the event. But when you can capture it before the event, I think those played a big role, but I can't answer your core question of what could we have done 20, 30 years ago
Okay.
that would allowed us to do this then.
Well,
It might be one of those things where you just need the right convergence of political, social, technical things
mhm.
to take place at the right time to where now you can make it happen. I don't know.
Well, let's talk about the sort of the cultural zeitgeist. You know, in Canada, the code conversation is focusing on the climate crisis and on energy efficiency, and that conversation is so urgent and so complex that we have a lot less time to talk about natural hazards when we're in building code meetings and committees and task groups and so on. So, you know, sometimes people who care about natural disasters, people like me, try to sneak resilience into the energy efficiency conversation just to keep it on the table, just say, hey, we're relevant too, and, you know, so on. Have you
Yeah.
thought about this overlap at all? And if so, what are your thoughts?
Yes, I have to a certain degree. In fact, part of my success at DWP that you're familiar with, but I'm not sure others are, comes from thinking about these multiple dimensions. And another factor that you could just bring in is deterioration. And sometimes that alone becomes the driving factor. And then, so in DWP, it was more of climate change, sustainability, and deterioration. But resilience and preparing for extreme events was not really part of it. But not a but so what I had recognized is a way to capture that, and that they were worried about how to replace all the deteriorating pipes because that was costing so much money in claims and lawsuits, that they needed to fix and get ahead of the pipe breaks. And so they started looking at innovative ways of using new materials and processes. And I said, well, why don't you include earthquake in that? Here's a pipe that actually does all of that stuff. And now we're incorporating resilience by designing with what we should have in the future rather than continuing to do what we did in the past, which was insufficient for resilience.
Mhm.
And they bought into that, which then led me to recognizing if we could somehow muscle in with these types of plans, now you can incorporate them along with energy efficiency when they're changing the energy systems.
Mhm.
It could easily be making them less resilient, but if there's a framework already at hand of which you just merge them, you know, when you're changing it, do it including this and use these materials instead of those materials,
Mhm.
or these construction processes instead of those construction processes, you can integrate them all together. So the hurdle is then getting this framework done in
Right.
a sufficient time that allows that to be merged. That's the problem with the process that I'm working on now.
Well, you know, I think that the pointy edge of the wedge there, the thing that you have to get into when you've got 30 seconds of people's attention, they're willing to stop talking about energy efficiency for 30 seconds. It seems like, you know, the thing that you say is, well, that, you know, this is all fine and important, but just make sure that you don't make society less resilient through these, you know, through these energy efficiency changes. So how do we ensure resilience as we make these big changes?
Yeah. And
But
here's a
this-
framework to help you do that.
Right.
Well, and I think it's important that you guys can bring these things forward in that context, because I always talk about, when I give public talks, and I do a lot of them, what I call Global Agenda 2030. It's the Paris Agreement. and the Sendai Framework for Action on Disaster Risk Reduction, and the Sustainable Development Goals and the Urban Agenda, etc. And I'm trying to make it too complex, but nonetheless, I think it's important that people understand the intersections between these.
Mhm.
And actually the Paris Agreement, which most politicians don't even seem to realize until you sort of browbeat them with it, actually has the objective of having national adaptation plans. And so when I'm meeting with politicians occasionally, I will bring out the point that we do have to reduce our emissions, but at the same time, we have to have an adaptation plan to improve our resilience.
Mhm.
And those two need to they do intersect both in the benefits and the costs and the ways of doing it. And we need to put those in a more integrated way and
Mhm.
deal with them that way. So,
Let me turn the conversation to yet another really interesting, a different dimension than what we've been talking about so far. Your functional recovery category B mentions vulnerable people. Vulnerable people, and it talks about their welfare and stuff. Now, vulnerable people might get their groceries from very ordinary buildings, the 7-Eleven. There are plenty of places in the United States where that's the grocery store. That's where you get your basic needs. And a lot of people live from paycheck to paycheck. So they can experience financial catastrophe if their workplaces aren't in, functional recovery category B, right? So, what do we do about those 7-Elevens and those really ordinary workplaces that are critical for the survival of an awful lot of people? And before I let you answer that, I want to add one more point, and that's that John Heinz and I had a conversation at the end of one of the oversight committee meetings in San Francisco a couple of years ago, 3 years ago. I've lost track of time. Where I made this point about 7-Elevens and people who live paycheck to paycheck, and he sort of threw up his hands and said, but if we recognize that, then virtually everything has to functionally recover fast, right? So, I mean, his complaint seemed to be that, well, if we recognize the vulnerability of vulnerable populations and their needs, then we can't have a multiple levels of functional recovery, as if the multiple levels of functional recovery was having those multiple levels was more important than the survival of these vulnerable populations. How have you, and so that was a couple of years ago, how have you dealt with that issue?
To a certain degree, but I'm not going to talk about it in terms of the building.
Okay.
I'm going to talk about it in terms of the services from the
Okay.
Lifeline system. So they would need electric power. They would need transportation, ways to get to and from the 7-Eleven. They would need water, likely. Maybe communications and natural gas might not be a big issue for them, although 7-Eleven might be supplying gasoline as a server, right, to help the community. So the way that I would look at it is it would not be the primary area of service, but you could take a grid. So break these systems down into grids of where you have different levels, A, B, C, D, you're picking up the B part. So make sure that you're able to supply to the A's. And it turns out the 7-Elevens are usually along the same corridors that would lead to a hospital. They're going to be on the major boulevards. And so if you lay out a grid for electric power or transportation or water, you're going to pick up, in my studies in LA anyway, you're going to pick up most of the 7-Elevens along that grid. So what we did first, Keith, is lay out, well, where are hospitals, where are the fire departments, where are the emergency evacuation centers, and let's make a grid so that we could ensure that that is a reliable pathway. We can isolate that grid from all of the damages
Mhm.
so that we can provide the services to those most important. Those are the A's. And then we said, where are the B's? And I didn't do it in terms of 7-Eleven, but I think essentially the same thing was dialysis centers. So you
Mhm.
get dialysis centers in the what do they call it? The supports for the hospitals, but you also have a lot of community businesses that provide dialysis in the corner lots, the corner basically same places you might find 7-Elevens, little business corners, and they're transient. And we would drive by, you know, 1 month and we'd see, oh, geez, what would we do for a dialysis center here?
Mhm.
And then we would come back to the same place 2 months later and realize, oh, it's not there anymore. It's a different business now. It's like,
Mhm.
well, we can chase these businesses. Now, 7-Elevens will probably be there for at least a decade, which is probably sufficient, maybe 30, 40 years. But if you lay this out in a grid where you cover the most important ones, and then you start laying, well, how do I change that grid for the second most important ones, which are the B's?
Mhm.
Turns out you've caught probably 90% of the B's by just getting the A's.
Uh-huh.
And then you might have a spur. So in this case, when I think of water, I would have a spur pipe that would be reliable that would go to the 7-Eleven. And so that wouldn't be our first priority, but the second priority that eventually around the city, we would get that put in. And a lot of the times the system might, well, geez, while I'm doing the A, if I only got to put in 2 blocks to get to the 7-Eleven and I already know that, I'll just do it at the same time. So now you're starting to capture this. And if I link that back, Keith, to your earlier question, you don't have to build this all at once because you can't afford to. But if you know you have to replace your assets, so the pipelines and the pumping stations are deteriorating, when a line along that stretch of that grid is slated to be replaced, put it in with the right materials so it will be resilient. You don't have to do it now. Do it over decades, not over years. And eventually the next generation or the generation thereafter will have this resilient grid and these resilient systems for a resilient community built out. But we can't think in short term. We have to think in the order of decades to centuries.
Absolutely.